Hey, this is Verbsky again. I just want to let you know we're switching into identities, which will take quite a while. So the class is going to slow way down. You'll be working just as hard, but section 10.1, 10.2 take an eternity to get through. So just be prepared that, like your MML assignment, yeah, it's going to take a while. And also know that, working it by hand and working it by MML, that's the big difference between an online course and, actually if you go to the class. So we'll get through it. Some of you will love identities. Some of you will maybe not like them so much. But really, we play this little identity game just to memorize our formulas. And that's what it's kind of all about. Speaking of that, recall. Now, when I say recall, worst word in all mathematics. We got sine theta, y over x, which, well, that would not be true. It would be y over r, which implies y equals r sine theta. And cosine theta equals x over r, which implies x equals r cosine theta. We know x squared plus y squared equals r squared, which implies r is the square root of x squared plus y squared. And of course we know tangent theta is y over x, but it's also sine theta divided by cosine theta. And similarly, cotangent of theta equals x over y equals cosine theta over sine theta. And not forgetting the reciprocals of sine, which is cosecant theta is r over y, and secant theta, the reciprocal of cosine, is r over x. But wait, there's more. The Pythagorean theorem identities, sine squared plus cosine squared theta equals 1 plus tangent squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. Now, these are fact. You can manipulate these all you want. These is what you know. Just get them down, get them memorized, because they're part of your foundation of trig. Now, I'm going to do a really easy one here. The graph of cosine looks like this. One more. Tick. 2 pi. Extend. And then we can extend back even farther. We say f of x equals cosine x is even, since folds about x-axis. Excuse me, that'd be the y-axis. Now, in algebra, this whole even and odd business was not necessarily helpful. It always seemed like a little bit of busy work. But you got to know even and odd is a big deal, because in trig, it turns out cosine and secant are even. The other 4 are odd. Now, here, let me quick explain secant. So, flip it over. If we could have chose a different color, that would have been smarter. Flip it over, flip it over, flip it over. You see it still folds about the y-axis. Now, algebraically, what it means to be even is f of minus x equals f of x. What it says is for some x here and some corresponding minus x, the y values are the same, i.e. they fold upon each other. So this is a great thing to know, because when I say cosine of a negative 45 degrees, poof, it's really gone. And of course I memorized this off the unit circle. It's the x coordinate, which is the square root of 2 over 2. Or you could memorize your special right triangle and say ka, and go 1 over the square root of 2, and then rationalize. But you see, if you put a negative on a cosine function on the angle, it just disappears. You know, basically pushing this problem into the first quadrant, which is really nice. It's a great option to have. And the same with secant of negative 60 degrees. Secant is even, poof. Secant of 60, which is 1 over cosine 60, which is on the unit circle, 60 is here, the x coordinate is 1/2, therefore 2. Because secant and cosecant are reciprocals, cosine's the x coordinate, secant would be the reciprocal of the x coordinate. Pretty nice. But the other 4 are odd, meaning sine basically looks like this, and it has sim with respect to origin. Nobody really ever likes this, but I'm going to explain it anyway. I take this piece and I fold it over here, and then I fold it these two over. So basically, if you had a piece of paper and you fold it in one direction, and then you fold the other direction and hold it up to the light, the graph is upon itself. That's how I see symmetry with respect to the origin. Call it the double fold, but most of the time, you know, if you're in quadrant 1, well, the same thing as in quadrant 3. I think you get the idea. But here's the thing: sine, its buddy cosecant, and cotangent, and tangent are sim with respect to origin, which implies f of negative x equals negative f of x, and that's the definition of being odd, is definition of being odd. So cotangent of a negative 45 degrees, cotangent's odd, rip it out, minus cotangent 45. Minus, now I got to figure out what cotangent 45 is, but it's 1 over tangent 45. Now, tangent of 45, there's different ways to do it. You can just turn and burn your unit circle, and if you got a good one, you have your tangents listed along the special angles, and it turns out you should be able to see a 1 there. So the answer is -1. You can draw your special right, 1, 1, square root of 2, and these are my 45s. You could have handled it right here if you say SOHCAHTOA or KAO. So adjacent over opposite with your eye on the 45, a 1 divided by 1 is 1, therefore -1. Or tangent of 45, you say TOA, and then you go opposite over adjacent, and you pick up your 1 again, and 1 over 1, -1. So being odd is a good thing. So what I'm trying to say is, with respect to our formula sheet, we got 6 more formulas. Cosine of negative theta equals cosine theta. Secant of negative theta equals secant theta. Sine of negative theta equals minus sine theta. Cosecant of a negative theta equals negative cosecant theta. Tangent of a negative theta equals negative tangent theta. Cotangent of a negative theta equals negative cotangent theta. These are part of your formulas. These you need to know. These 3, all I say is sec and cos even, and then I actually know all 6 of them. But then you got to know that even means poof, and basically odd means rip it out. Okay, now today's talk, I'm going to go through the book and example by example, and then I'm going to, hit my 40 minutes, and then I'm going to work some problems directly out of the book. And it's going to take a while. So basically, I'm thinking I'm going to have, basically 2 or 3 lectures over this section. They will help, and you got to kind of watch somebody do it so you know the game. It's like Sudoku. If nobody ever shows you how to play it and all that, well, you don't really, I'm just saying you kind of need the directions here. It's a little game we play when we prove identities. So example 1, page 727, right out of the text. Express cosine x in terms of tangent x. Well, we know 1 plus tangent squared equals secant squared x. So secant squared x is 1 over cosine squared x. Now, this is an equation here. Now, equations, you're allowed to do the same thing to both sides. So I'm going to conveniently forget about this right here. Now, you know how I usually multiply both sides by 2/3, you square root both sides. Well, this is a new cool rule. Reciprocate both sides. Okay. Yes, so reciprocate both sides. And you get this. And you get cosine x equals plus or minus the square root of 1 plus tangent squared x. And then we're done. That I was able to relate cosine to tangent. That's all I want. Example 2. Write tangent theta plus cotangent theta in terms of sine theta and cosine theta. All right, so tangent theta plus cotangent theta equals sine theta over cosine theta plus cosine theta over sine theta. And technically we're done. We did it. Tangent and cotangent are now sines and cosines. But now we need to simplify. Now, I don't know if you know this, but you could have always added fractions like this. 5 plus 6 over 10 criss it plus cross it and apple sauce it. Now, as long as the 2 and the 5 don't have anything in common, I just do this all day long. So, sine squared plus cosine squared over sine theta cosine theta. Now, sine squared plus cosine squared is 1 by memorization. Sine theta cosine theta. And I even have a better expression than I had before. It's simpler. Now, just so you know, I could keep going. Like, but, I'm not supposed to, but I'm the teacher. I can do what I want. You can go times 1, and you could have went cosecant theta, secant theta. Because the reciprocal of sine is cosecant, the reciprocal of cosine is secant. You could have went cosecant, secant. If they asked that, but that would have been cool. All right, so now we're going to start identities. Identities just means both sides are identical. Are identical. Now, they're going to say verify cotangent x plus 1. By the way, this is example 3. Equals cosecant x cosine x plus sine x. Now, when you do verify an identity, you need to prove that both sides are identical. But there's rules. You can work from right to left, left to right, but you can't really work it like you work in an equation. You can't work on both sides at the same time. So this is why we're here so long. Now, some of these are like one-steppers. Some of these are 7, 8, 9 steps deep. Can I get stuck in a problem? Sure. Even I can get stuck. I'm pretty old to be getting stuck, but sometimes I do. So what I like doing is I like doing PF, standing for proof. Now, I can start with the left side, or I can start with the right side. Now, I choose to start on the uglier side most of the time, so I'm going to start on the right. And then I'm going to do obvious algebra move. I'm going to bring it. It's called distribution, but it's more fun to say bring it. Anyway, I get a cosecant x cosine x plus a cosecant x sine x. There's something really special, because these are reciprocals. Like 2/3 times 3, half, boom, 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 boom. You always get 1. Cosecant is 1 over sine, and those sines cancel, you get 1, but reciprocals cancel, so you're just allowed to go plus 1 in this class. Now you see, I got my plus 1. I'm making good progress here. Now, if I can only prove that this stuff right here is cotangent, but I know cotangent, move this downstairs to 1 over sine x. So technically you're multiplying by 1 over sine x, and 1 over sine x times cosine x is cosine x over sine x. So basically I skipped a step. But bottom line, you just push this downstairs to the denominator, it becomes a sine. And therefore, I get cotangent x plus 1, because cosine over sine x is known. Boom. I proved it. There's an identity. Pretty good proof. I'm kind of a step skipper here and there. But after about 50 of these, you'll have it down. Let's see what the book has cooked up for us. Now, just so you know, I don't always do what the book does. I got my way to work these problems. They got their ways. Their ways are pretty good. sometimes I find them a little inefficient, and they use a different trick than I would use. But anyway, here we go. Here's the problem. Tangent, I hate it. They use a t. I refuse to use a t. I'm going to use an alpha minus cotangent alpha over sine alpha cosine alpha equals secant squared alpha minus cosecant squared alpha. Whoa, this looks scary. Proof. There's a left side and there's a right side. Okay, so what I'm going to do is I'm going to convert everything on the left to sines and cosines and kind of hope. So the left side's going down, but I'm going to go sine alpha over cosine alpha minus cosine alpha over sine alpha over sine alpha cosine alpha. Now, keep in mind, you can't work on like both sides at the same time, because nobody's telling you can't work backwards. And you usually wreck your paper. The secant squared alpha minus cosecant squared alpha. Now, since I've switched everything to sines and cosines on the left, I'm going to go 1 over cosine. Whoa, something happened there. 1 over cosine squared alpha minus 1 over sine squared alpha. Now, as I say, I'm like the crisscross applesauce freak. If these have nothing in common, I go sine squared alpha minus cosine squared alpha over cosine squared alpha sine squared alpha. Now, I'm starting to look here, and I'm not quite sure where I need to go, because this thing is not simplified like this. So now I go back to the top, and I go crisscross applesauce, and I get sine squared alpha minus cosine squared alpha over cosine alpha sine alpha, criss it, cross it, applesauce it, over sine alpha cosine alpha over 1. Now what I'm going to do is I'm going to copy dot flop. So I'm going to go sine squared alpha minus cosine squared alpha over cosine alpha sine alpha times 1 over sine alpha cosine alpha. Remember, you must copy the top, dot it, flop it, or invert and multiply, and I net in the middle. Those two things are exactly the same. I get to reward myself by making a little square box, which means end of proof. Remember, you can work from left to right, right to left. You can do what I just did, right, left to right, and right to left meet in the middle, but you cannot work at both sides at the same time. That was fun. Now, just so you know, I didn't like these when I was young. It's taken years to get really good at this. Example 5. Step 1 is actually memorizing all the identities you need to know. That's the trick. So when we say recall, you need to recall all that stuff. And here's 1 minus sine x. I'm going to do it on time, 16 minutes to go. 1 plus sine x over cosine x. So basically what I'm telling you, you're probably not going to need to read the section because I'm going over it. They do have a few things in there that you might be able to pick up some extra stuff on. Or maybe they would just work it differently than me. I'm not going to check that. Oh, I know this trick. Now, The bad thing about identities is there's so many algebraic tricks. So, that's why you're here. This is a standard trick. I don't know what side to start on, literally. In my opinion, I like the right side better than the left side, because if I felt like it, I could split this up with one term on the bottom. Here, let me explain this. I know I can split this up into 1/3 plus 2/3. So that's really nice, where on the left side, algebraically, you cannot, split it up. That's bad. Can't do that. But I'm telling you, it's not going to matter, because I know what the trick is here. We're going to go proof. There's his left, this is right. I'm going to start on the left and write it down. There's no algebra to actually do. There's nothing you can do. But you can make up algebra, multiply by its trigonometric conjugate. We're going to multiply by 1. Well, hey, look, that gives me this. I'm looking for that. So we're off to a good start. So you multiply straight across, and you get cosine x times 1 plus sine x. Now, when you multiply conjugates, if you go FOIL, here, let me explain, like 1 minus x, 1 plus x, you go first, outer, inner, last, you get 1. The outer is x, the inner is minus x. The OI, FOIL, minus x squared. The OI cancel. So when you got conjugates, it's not really a FOIL. It's a FL, a first last. So it's just first, last. That's all you have. So it's just 1 minus sine squared x. When you multiply by a conjugate, you intentionally multiplied it so the outer inner terms cancel. So you're allowed to multiply by 1 anytime you want. That's what I did. Oh, but you know what I know? I know that sine squared x alpha, cosine squared alpha equals 1, and 1 minus sine squared equals cosine squared. So that's known. You're allowed to use that one and all variations thereof. I erase it. Okay. Where am I going? Oh, I just want a cosine. Oh. Cross off one of, whoa, not like that. Can I edit and undo that? There we go. Cross this off, cross one of those off. Equal to right. Reward myself with a square box. Woo! Well, I find this hard to believe, but the book says if I do 2 more examples, you are competent. I do not trust them at all. So it looks like I'll get my lecture done, and then I'll just work some more problems right out of the book. But E6, whoa, secant alpha plus tangent alpha over secant alpha minus tangent alpha, 1 plus 2 sine alpha plus sine squared alpha over cosine squared alpha. Proof. Now you look at the left, you look at the right. Now you could go yard sale on this and convert everything to sines and cosines and just go crazy. I've seen this happen before. I don't know if you remember, like if you got 1 plus x and 1 plus x, you get 1 plus xx plus 2x plus x squared. See the 1, the 2, the 1, the 1, the 2, the 1. I think something like that's going to pop up here, like 1 plus sine x, 1 plus sine x. I'm pretty sure something like that's going to happen to us, down the road here. But I'm going to start on the side that with the secants. So I'm going to start on the left. Now I'm sitting here contemplating, I'm kind of old. I was thinking about multiplying by like a secant alpha plus tangent alpha, a secant alpha plus tangent alpha, because there's this formula, tangent squared alpha plus 1 is secant squared alpha. I was hoping that that might, pop up, and then I'd be able to avoid what I'm about to do. See, I'm old. I don't know quite what to do, but I'm going to try the number one go-to move. 1 over cos alpha plus sine alpha over cos alpha. 1 over cos alpha minus sine alpha over cos alpha. Whoa, these have the same common denominator. That's 1 plus sine alpha over cosine alpha. These have the same denominator. Now, I'm not even looking to where I'm going yet. I'm going to get a 1 plus sine alpha over cosine alpha times a cosine alpha over 1 minus sine alpha. And I get a 1 plus sine alpha over 1 minus sine alpha. You're like, whoa, this felt like a good move. But you're looking and you don't have it. And you work yourself into a spot where there's absolutely no algebra to do. But you can multiply by a conjugate. And I'm going to multiply by the conjugate of the denominator, which is 1 plus sine alpha, and 1 plus sine alpha. Because I said that might come into play, I know I'm going to get my numerator, and I got to multiply out my denominator. So I get a 1 outer inner, you get a sine alpha, a 2 sine alpha, plus a sine squared alpha, over a 1 first last, minus sine squared alpha. So I picked up what I needed to pick up on the top. And on the bottom, I know that's cosine squared alpha. Why? Because sin squared, excuse me, I'm not supposed to say sin. Sine squared x plus cosine squared x equals 1. 1 minus sine squared x is cosine squared. It is known. End of proof. Latin, QED. There's 6 of 7 right out of the text. Here comes example 7. By the way, I didn't work at anything like what they worked at, so if you want to check their work, go ahead. I totally dominated them. I didn't like. Oh, they turned around and worked it 2 different ways. Neither were the same as me. So go ahead, read it up. Oh, example 7 is just applied. I don't want to get into applications now. We're going to be stuck just working basic identities for now. Now, if you want to risk it, go ahead and start your homework. I think I put it like a crazy due date, like October 1st. I don't really know what I want to do there. I'm thinking October 1st is reasonable. but you know, I'm going to make multiple assignments due October 1st, and you can't work the next assignment until you finish the first assignment. So, you know, you got to pace yourself. This is one of these things where you're just not going to do overnight. This section 10.1 might take you, you know, 10 hours to finish section 10.1. You know, and you're starting to figure out MML is not your friend. It's brutal sometimes. So don't worry, I'm working it with you, by the way. So don't be feeling like I'm abusing you. I got to go through the exact same abuse. I'm 52. I can take it. You're young. You should be able to take it too. Anyway, I'm going to end this lecture, and then I'm going to create another lecture, but it's going to be selected problems right out of the textbook, and a lot of identity work, trying to make sure that you see all the tricks. And then if you watch what I do, some of my tricks are actually different than the book tricks. So between the text and the MML and their solutions, my solutions, technically you should end up, you know, down the road here being better off than I am. You know, I only got so many moves where if you pay attention to the book, you know, you can, you know, actually use their moves. Although half the time inefficient, you know, they are still moves. I always say if I need to pound a nail into a corner, it'd be good, you know, 7 different ways to do it, because if you ever tried to pound a nail in a corner, you know, it's kind of not a good thing, you know. So having multiple methods is always good. Anyway, see ya.